The first construction is the constant functor, where the type Z must be a monoid. Now, this is exactly the same as we just had here, the construction 6. And in fact, construction 6 was examined, and we have found construction 6 as follows. We have verified the laws, but we did not actually use the fact that the type constructor was considered to be a functor. So we could have defined exactly the same code without using this type class instance of functor. And in fact, I have defined also type class contravuzip, which is the same methods, except it expects a contrafunctor instead of functor. But other than that, it's exactly the same type signatures. So the result is that we actually don't need to prove any more than we already have. The previous proof goes exactly the same, word for word, for contrafunctor here as it went for the functor, because we never used the fact that we consider this type constructor to be a functor. Well, this type constructor is, of course, somewhat trivial. It does not depend on the type A. But exactly the same logic will apply to many of our constructions that we just considered for functors. For example, the product construction is of exactly the same kind. The product construction is defined here for functor, but we actually don't use the functor instance as a constraint when we define the zip and the wrapped unit. And if we look at the proof for associativity and identity laws, we never use map in any of these proofs. We actually never assume that G or H are functors. We assume that, for example, equivalences can be established between these values. But these equivalences can be established for contrafunctors equally easily as for functors. So, for example, for a contrafunctor, if you want to convert, for example, C of A, B, C into C of A, B, C, like this. This is an equivalence that is required in proving associativity for certain functors or constructions. What you need is a function that goes the opposite way from here to here. And of course this function exists. It's a trivial reordering of the tuples. Whereas for functor, you needed a function that went in the other way, but also that function was trivially available. So there is not a problem going through exactly the same proof and just substituting this kind of equivalence, which is exactly similar, whenever we need equivalence between nested tuples and also the equivalence between a tuple with unit value. And a single value, which is necessary for the identity laws. The non-trivial construction is this one because there's no analog of this construction for applicative functors or for monads, for that matter. As we have just seen, in general, the disjunction of two applicative functors is not applicative in all cases, and disjunction of two monads is not a monad in all cases. So let's look at the implementation of this construction. We use the CATS library for Contravariant, which is their name for contrafunctor. And we define this type constructor as an either of G and H. Assuming that both G and H are contravariant, then this is also contravariant. This is how we establish that. We define contramap. So contramap should map A to B using a function from B to A. Well, this goes exactly like in the functor case, except we use contramaps instead of maps. So if we're on the left, we use left, and we map in the G contrafunctor. If we're on the right, we return right, and we map in the H contrafunctor. So now we can use applicative instance, and we will use both contravariant and contra-applicative type classes. We actually will need that. Here's how it goes. So the wrapped unit first needs to be defined. So that's a value of this type. Now here we could return a left with wrapped unit of G, or we could return a right with wrapped unit of H. And actually, this choice is arbitrary. We could return a left, or we could return a right. We could then define the zip accordingly, and laws would hold. The reason this is so is because this construction is completely symmetric. There's no difference between G and H. And so if we are able to define things with this choice, then just by swapping G and H, we would be able to define this construction with the right choice. So let's make this choice arbitrarily so that we're on the left with wrapped unit. So now, how do we define a zip? We need to transform this and this into this. If we are on the left, then clearly we just return the left. We have two lefts, G of A and G of B. We can just zip them together using the zip from the G contrafunctor. And if we're on the right, if both of them are on the right, we can just zip in the H contrafunctor. So that's clear. Now what do we do if one of them is on the left and the other is on the right? Well, we need to return either left of G or right of H. What do we do? Well, we have now seen two cases when we had a disjunction and we implemented the zip function for disjunction. In each of these two cases, what we had to do is that if the wrapped unit was on the left, then the mixed case needs to be on the right. If the wrapped unit is on the right, then the mixed case needs to be on the left. And that was kind of the pattern that we have seen in the previous two examples. So let's follow that pattern. and we'll see that this actually works. So how do we return a right of HAB? Now we have only an H of B, and we have also a G of A. Now we can't possibly combine G and H. There's no method for that. So we have to ignore G, and we have to transform H of B into H of AB. But that's possible. H is a contrafunctor. So we can contramap it with this function that transforms AB. I called it X and Y here, but it would be easier maybe to read the code if I called it A and B. Because then the types would be more clear. So I always have this function that transforms AB into B. It actually ignores A, so I can kill that. And that function, transforming AB into B, contramaps HB into H of AB. And that's what I need. I need to transform HB into H of AB. And so that's why this code has the right type. And I do the same thing in the other mixed case. I return a right of HA, and I contramap it like this. So I transform HA into H of AB. So having implemented it, let's check the laws. How do we reformulate it? So if we consider this kind of combination, if all of them are on one side, so all three on the right or all three on the left, then we can do immediately we can see what happens. So it will be either on the right of HA, HB, HC all zipped, or on the left of GA, GB, GC all zipped. So that's clearly associative. So, because we are now doing zip in the functor H or in a functor G, and that's associative by assumption. Now, if some of these are on the left and others are on the right, and according to our code, all the left ones are ignored, and all the right ones are contramapped so that they have the right type. And the contramapping is just with the trivial substitution of tuples. So clearly, all the right ones are going to be just converted to this using the trivial contramap and then zipped together. And so the result would be something like this. It will be a contramap with this, where, let's say, C was on the left, so it was ignored, and A and B were on the right, so they were not ignored. And then we need to zip them. So that's associative because the condition that we are ignoring all the ones on the left, that condition is independent of the ordering. We just, no matter what parentheses we put in first, around these two or around these two, the condition of dropping all of these that are on the left, that's associative, not independent of the order of parentheses. And then we will contramap it finally into this type and zip them all together. That's associative as well. Probably the zip H is out of place here. Yeah, now identity laws are actually checked using an explicit computation, because you cannot just argue about it out of some symmetry consideration. You have to actually compute and verify that our intuition was right, that we had a left here, therefore we need a right here. Let's check. So let's take some arbitrary FA and zip it with the wrapped unit, which is this. And the result is that we need to match, according to this code, we need to match like this. Now only two cases remain because we have a left here. If they're both on the left, we do a zip. Now this one, GB, is actually this. So that's going to be equivalent. If it's on the right, then we're actually ignoring this GB, according to our code, because we need to ignore this. And we are on the right. We do a contramap, which is like this. And this is just a contramap that is the isomorphism, or the equivalence, that we allow. So that's the equivalence expressed by this symbol, as I'm using it. And that's equivalent to right of HA. Because contramap with this isomorphism is precisely the equivalence. And so then right of HA here, we have a right of HA here. So identity laws hold. So clearly this would not hold if we didn't have a right in these two places. So in this way we verify this construction. Now this construction says that for any functor and applicative contrafunctor G, this function is applicative as contrafunctor. Let's see how that works. This is the type constructor, so as a type function. It's contravariant because obviously this is a functor by assumption. H is a functor. And this is a contrafunctor, so the contrafunctor is here in a covariant position, and the functor is in a contravariant position. So the result is contravariant. To implement that contravariance is easy. You return a function which takes hb. Now you have to compute some g of b. So how do you do that? You can get g of b if you first get g of a and then contramap it with this. So how do you get g of a? You just substitute into fa some h of a. But how do you get h of a? You take h of b and map it with f, because h is a functor. So that's what we do. We map hb with f, substitute that into fa, and then contramap the result with f. And this could be generated automatically for us. Now let's implement the zip. Now we are using the functor instance on h to do that. But we're actually not using the contravariant instance on G for this. Let's delete this. We are not using contramap in this code. We are using map on H. So we need the functor constraint on H, but we don't need contrafunctor constraint on G for this code. The wrapped unit, it's a value of this type. So how do we generate a function of this type? Well, we can take some h of unit, but there's no way for us to use that h of unit to make g of unit. We already have g of unit anyway, it's the wrapped unit, so let's ignore the argument and return that wrapped unit. How do we do zip? So that's a bit of a complication. We have an h of a to g of a, h of b to g of b, and we need to return this function. So let's return this function. So we return a function that takes HAB and returns GAB. So how do we get a GAB? Well, clearly we need GA and GB for that. So we need HA and HB so that we can substitute those into FA and FB. How do we get HA and HB? Well, we take HAB and project out, say, the B. We drop the B. So that's just a map with this function that drops the B out of a tuple. We could write this function more concisely like this in this column. But anyway, so that's how we do that. So now we get HA, we get HB, and we obtain G of A, we obtain G of B, and we zip them in the contrafunctor G. We're done. The type is correct, but it seems like it was the only possibility to implement these types. Let's check the laws. So here it's hard to reason about these values in some hand-waving fashion and reformulate them explicitly as manifestly applicative. Manifestly associative. It's hard. Let's write down the code. So let's consider this expression first. So this expression has this type, from this to this. We write down those things. We just inline. I just inlined HAB map 1, HAB map 2. I inline them. So let's now zip this with FC. So that would be more complicated. We have FA zip FB, and then we have apply this function, because this is this, to HABC map 1, zip FC, HABC map 2. So if we just substitute the definition of zip again, then we have this expression. Now, notice we have here HABC map 1, map 2. Map 1, map 1, map 1, map 2, and HABC map 2. Now, our HABC is actually of this type, so it has a nested tuple. Let's simplify that. Let's map this HABC as the flat tuple and convert it into our non-flat tuple first. So we convert it, and then we would have these expressions, which are basically just taking first element of this tuple, which is this, and then again taking the first element, which is this. So this is basically projecting ABC onto A, which is going to be equal to that. So that simplifies our expression into this. And then we contramap the result in this way, so that we that will transform the nested tuple back into non-nested, since it's a contramap. So here's the code that results from this operation. We start from HABC, which is flattened, and then I just substituted all of this. I contramapped at the end, and then I have simplified these things. So I have FA of this, zip FB of this, zip FC of this. I think I have. And so I first have two zipped together, and then I zip it with this FC. Now the last step is actually zip in the G contrafunctor, because this is a zip between values of f of something, and f is a function from h to g. So this zip is associative, and I'm just applying some kind of an isomorphism, which is equivalence. And, don't care about that. I can always apply it whenever necessary. And so the main result is that I have here this expression that is manifestly associative by assumption, because this is a zip in the contrafunctor G, and everything else is perfectly symmetric. So FA, HABC map 1, FB, HABC map 2, FC, HABC map 3. So there's no asymmetry. And so I expect when I start with the other order of parentheses to get exactly the same thing with different parentheses. And so then, because of associativity of G, these two are equivalent. And these two, of course, I can always add or remove whenever necessary. So that verifies the associativity law. And let's look at identity. The identity law is that this zip of some arbitrary FA with this function that we define that always returns wrapped unit of G, ignoring its argument. So let's find out what that does. So the code is like this. So we have some HA and HB that we define right here. And then we do FA-HA, zip, FB-HB. Now HB is actually this, but it's the function FB that is acting on it is this function that ignores HB. So HB is actually ignored. And the result is always this. So the result is going to be FA-HA, zip this. Now this is the zip in the G contrafunctor, which we assume satisfies the identity law, and therefore this is just mapped into G of A into G of A unit, which is the isomorphism. And so basically we start with function FA, and we have a function that takes HAB, maps it into HA, and applies FA to that. So that's basically, if you look at how it's mapped using this isomorphism, which is going to be the isomorphism between A, comma unit and A. So that's our equivalence. And so that's basically HAB is equivalent to HA, therefore. And so FA of HA is the same as FA of HAB, well, up to equivalence. And so we take FA and we return a function that takes HA and applies FA to HA. So we take FA, return FA. So that's identity. So therefore, this returns a function that's equivalent to FA up to the isomorphisms that we have, such as this one. And so the left identity, the right identity holds that we just found, and the left identity holds in the same way, just HB instead of HA. So much for this construction. Now this construction is a functor G and a contrafunctor H. So if we look at the corresponding construction for functors, this one, you see we are not using the functor on G. We're using functor on H. Actually, I think that is a typo. This is a mistake. So we use a map on G. G must be a functor. but we are not using map on H. So we can delete this. We don't need type constraint that H is a functor. And when we check the laws, we use map, but always on G. So we take out these maps, but these are values of the functor G. So we never use map on H. And here also we use a map, but only for G. We never use map on any values of H. And because of this, the proof that we gave for this construction for functors, where G was a functor and H also a functor, now G must remain a functor because we're using map on G all over the place. But H doesn't have to be a functor, it could be a contrafunctor. And so this construction is very similar to this one, and the proof goes through exactly the same because we don't actually need the functor property of H. We only need the applicative property, but not the functor property. So we are not using map or contramap on H at all. We're only using zip and wrapped unit. The proof will go through exactly the same word for word. So these are the constructions that I was able to find for contrafunctors. Now, the interesting thing here is that we have constructions that have constant functor. We don't have identity functor because it's not a contrafunctor, it's a functor. But we have a constant contrafunctor. We have product, disjunction or sum, and function or exponentiation. So we have exponential polynomial constructions. All of them are here. We also have composition, but this is not necessary. If we have these three constructions, we can build up an arbitrary exponential polynomial contrafunctor with monoidal coefficients, as long as we have these, all the constant types that occur must be monoids. So this is what it means to have constant coefficients for exponential polynomial contrafunctors. And then we have covered all possible contrafunctors. So essentially, all exponential polynomial contrafunctors with monoidal coefficients have an applicative instance through these constructions. So as long as we found any exponential polynomial contrafunctor with monoidal coefficients, we know it's applicative. There's no question. There are no counterexamples of non-applicative such contrafunctors. So this is very interesting. So we did not have this for functors, that all exponential polynomial are functors. But that's the example I have seen. So I was trying to do counterexample. So this is a counterexample for functors. This is not applicative. But if you reverse these two arrows, you get a contrafunctor, and it's applicative. And we have seen that. It had implementations, and we know why. It's this construction. So the conclusion is that all applicative contrafunctors that you can write down are going to be exponential polynomial contrafunctors, and vice versa. All the exponential polynomial contrafunctors are going to be applicative. Now, let's talk about profunctors. In the first part of this chapter, we have seen type constructors that are not functors, but applicative. And these were actually also not contrafunctors. And there are two main examples that we have seen. One was the type class for monoid, and the other was the fold, the type class for fold, or rather the type, just the data structure for fold. We had fold fusion, and the data structure for fold, the first variant of it was neither a functor nor a contrafunctor. And yet it was applicative. We could have an applicative combinator for it. So those are profunctors. Informally speaking, profunctors are type constructors that have the type parameter, and the type parameter occurs both in contravariant and covariant positions. Because it occurs in both of these positions, you cannot have a map and you cannot have a contramap for this type parameter. Here are some examples. Typically, this would be an example. So you have a function from this to this, and the type parameter occurs both in contravariant and in covariant positions. Another example, you have a disjunction or sum type, sum of a and a function. But so here a is covariant and here a is contravariant. And so these are typical profunctors. What would be an example of a non-profunctor? Well, clearly, anything you can write using exponential polynomial operations is going to be a profunctor, because the type parameter is going to be either on the right or on the left of the function arrow. And the only way to have a non-profunctor is to have a non-exponential polynomial type constructor. An example of this would be a so-called generalized algebraic data type, which I find not a helpful name. But these are basically, I would say, these are type functions that are partial type functions. We have seen that concept in the chapter on type classes. These are just partial type functions. They are not defined on all types. They're only defined on certain types in some specific ways. And here's an example in Scala. So you have a trait which is parameterized by type A, but there are only two case classes that implement this trait, and they have specific type parameter values here, int and unit. And so it means you cannot instantiate a value of type, say, f of double. It's impossible. You can only instantiate f of int and f of unit. And as a result, you also cannot instantiate f of a for arbitrary a. And so there's no hope for you to have map, contramap, or anything like that. Because map and contramap would require you to be able to transform f of a to f of b for arbitrary a and b. And you can't even instantiate those f of a and f of b for arbitrary a and b. And so no hope for that kind of property for these types. So these are partial type functions. No hope for them to satisfy good properties. I'm trying to invent a good notation for these kind of type functions. I'm not sure this is good notation, but this basically means a string, but it is ascribed this type f of int, and an int, but it's considered of type f of unit. Just by hand, we just say this is f of unit and this is f of int. Maybe this notation is useful, but in any case, at this point, I have very little to say about these partial type functions, except that they are not profunctors. This is an example of a non-profunctor. Now, notice I have not yet actually given a good definition of a profunctor. I've illustrated what I want to achieve. These kind of things are profunctors that have a in a certain position. But this is not a good definition because it depends on being able to write a type in a certain way. And what if we don't know how to write it in a certain way? Maybe, what if this is actually a profunctor, just I don't know how to write it correctly? We need a better definition, a rigorous definition. Oh, there's a typo. I'll fix it. A rigorous definition of a profunctor, which is that it is a a type function with two type parameters such that it is a contrafunctor in A and a functor in B. So A is contravariant and B is covariant. If such a type function exists, that PA is defined like this, when we put A and A to be the same type, then that type function is a profunctor. So for each profunctor, there must be a way to split it into a type function of two type parameters. One of them is strictly contravariant and the other strictly covariant. And if you can do that, then defining P like this, then P is a profunctor. That's the definition of a profunctor. So obviously we can do this here. We can say, well, this is going to be A and this is going to be B in the Q. So we define Q of AB like this. So Q is 1 plus int times A going to B. And here we put here B because this is covariant, and here A because this is contravariant. So that will become the Q that corresponds to the P. So basically, the idea of this definition is that a profunctor is a type function where really you can split it into a function with two type parameters, each purely covariant or purely contravariant. And that's what. And then obviously for the contravariant you have a contramap. For the covariant you have a map with the laws separately holding for A and for B, with the usual laws. Since you have that, then you can apply something called xmap, which is just a combination of map and contramap, map in B and contramap in A, except that then after that you set the same type parameter. The result is that in order to map a profunctor from one type to another, you need functions from A to B and from B to A, going in both directions. And if you have that, then you use this in the map, you use this in the contramap for Q. It's a bit confusing here. I use A and B both for this and for this. So I will fix this. Here I would use this as x and y instead of A and B. I would have say x and y, and px is, or pa is qaa still, but this is going to be x and y. So then this A and B plays a very different role from this. So because we assumed that Q exists, and so it has a map and a contramap, then obviously P will have an xmap, what is called in the Scala Z library. In the CATS library is called IMAP. Not sure what is a good name, but let me call it xmap. So this will be defined. This follows from the definition and the laws, identity and composition laws. Oops, there's a mistake. There must be G2 followed by G1, because the composition for the contravariant part is the opposite order. Okay, so I'll fix that in the slide. So this is G2 and G1. The important idea is that once you have this Q, it means you already have map in B and contramap in A, and the laws for those hold separately. And so it can be derived that these laws hold, because they're just compositions of those functions. And so, therefore, these laws can be seen as a consequence of this definition. And it's not a new assumption or a new requirement. It's a consequence of the definition. And so that's why we believe it's reasonable to impose these laws. So as I said, all exponential polynomial type constructors are profunctors, because in all of them there will be type expressions of this kind. The type parameter must be either on the right or on the left, and so then you can easily relabel the covariant and the contravariant by different type parameters, and then you can define the Q that you are required to have, and then you have your profunctor defined, and you prove that easily that it is valid. Applicative profunctor is defined in exactly the same way using zip and wrapped unit with the same laws. There's no corresponding app method, but there's a pure method from A to PA, because you can take wrapped unit, which is P1, and you can XMap it with a function from A to 1 and a function from 1 to A, which you will always have. Since you have an A, then you have a function from 1 to A, and a function from A to 1 you always have. And so you can XMap your wrapped unit from P1 to PA, given an A. So that's the pure method. But you cannot derive app, or any analog of app, I believe. So what are the constructions? All the previous constructions still work, because profunctor is a superset of both functor and contrafunctor. Any functor is a profunctor, any contrafunctor is a profunctor. It's a superset of both of them. So all of the constructions we had before also hold as profunctor constructions in a trivial sense. However, there are more constructions. So the product construction again, then there is the monoid addition, then there is the free-pointed, and a function. Now, a function works, and all these constructions work in exactly the same way as they work for the functor. And this works in exactly the same way as it works for contrafunctor. You see, here it's a functor here. It's not contrafunctor, it's a functor. It's important. It doesn't seem to work for contrafunctors really, or for profunctors. I tried, but I couldn't make this construction work. I could implement the types of zip and the wrapped unit, but I could not get associativity law to hold for this kind of construction. So I don't think this construction works, but these constructions certainly work, and the composition also. In order to find that they work, you don't need any more proofs, actually. You just look at your old proofs, and you find that you aren't using the property of G as functor or contrafunctor or anything. You don't use map on G when you do these things. You don't use contramap either. In this construction you use pure. But you have pure for the profunctor. In this construction you use only zip and wrapped unit and nothing else. In this construction you only use zip and wrapped unit. In this construction you use a functor for f, but you don't use anything for q except wrapped unit and zip. And similarly here. And so all these constructions actually go through with no further proofs necessary. I was able to find out that these constructions work by pretty much trial and error. I hope I found all the important constructions that exist. The proofs, so for example here we use map on H, but we don't use anything on G. We only do map on H, but never on G. So I'm pretty sure that this construction does not work. and I'm pretty sure these constructions all work, because these proofs do not use properties of profunctor other than zip and wrapped unit. Let me just check the sum of A and G of A. So this is construction that uses pure. So let me just look at the proof of that construction. Here it is. It does not use the functor instance on G. It just uses the zip and wrap unit. There's never any map. There's a pure. So we need a pure on G. That's true. And it needs to satisfy identity law. That's true. Other than that, we do not use map on G anywhere. So we use the equivalences, yes, but those are available for profunctors. In the same way they're available for contrafunctors. We can, for example, use xmap and rearrange tuples in the forward direction, in the backward direction, and then this will give us a rearrangement of tuples in the type of the profunctor. So to summarize, these are the constructions I believe exist for applicative functors, contrafunctors, and profunctors. Now, I'd like to have a little comment on an interesting property of applicative functors, which is symmetry, or commutativity. But I prefer symmetry because it's not really commutativity. Literally speaking, monoidal operation can be commutative or symmetric with respect to its arguments. It's probably better to say commutative. It's just this property. Now, if you want to apply the same property to zip, so I would use this notation for the zip operation, you cannot literally say that FA FB must be equal to FB FA, because there are different types. So you need to map the types by rearranging the types, because this is going to be of type f of AB, and this is going to be of type f of BA. But if you implicitly say that this isomorphism is included in the equivalence, then you could write it like this. So that is the symmetry property. Now, not all applicative functors are symmetric. What does it mean that it is symmetric? Well, it means that the effects somehow are independent in such a way that the second effect is independent of the first. Now, in the applicative functor, the second effect is independent of the value returned by the first container. Of the value, it is independent, but it may not be independent of the effect. And if it is so, then this symmetry will not hold. But there are some examples where it holds. For example, list is symmetric, manifestly so, because you can just permute the list elements. A good example of non-symmetric applicative functor is parsers. We have looked at this briefly. Parsers are not symmetric because when you do applicative composition of parsers, the first parser already might have consumed some part of the input string, and the second parser starts from the place left over by the first parser, when the first parser stopped. And so the second parser depends on this effect. Now, the value returned by the first parser does not indicate necessarily the position where it stopped. The value is the value it parsed out of the input. And the second parser is independent of that value, but it depends implicitly on where the first parser stopped. And so the parser combination using applicative composition would not satisfy this requirement of symmetry. Also, if you define anything through the monad, most likely it's not going to be symmetric. Well, for lists, we know it is not symmetric. We have seen that. The order is different in the result when you define zip through the monad. But we know that for lists, the monad-defined zip is not usually what you want. You want applicative-defined zip, which is incompatible for lists. All polynomial functors with monoidal coefficients that are symmetric will be symmetric applicative functors, because we have seen how polynomial functors combine their values. So the monad zip would permute these elements in a different order if you change the order of these two. So the monad zip is not symmetric. Now the polynomial one is symmetric because it basically combines elements like this. And so if you put this first, it doesn't matter. We'll still take these two and combine with these two. So similarly here. So the typical polynomial functor with symmetric will be with symmetric monoidal coefficients, like the integer, which is a symmetrical monoid Boolean or symmetrical monoid. Strings and string concatenation is not as a commutative monoid. So that would not be commutative, and so the polynomial functor with string coefficients would not be symmetric or commutative, maybe better to say. But I've seen usage of the word symmetric, so I would say commutative or symmetric applicative functor would be probably the same meaning. Now, it's interesting to say that, first of all, most of our constructions preserve symmetry. So if you think about how we defined all these constructions, at the last portion there was zip in this functor, and it was symmetric in how you provided arguments for this zip. So if G is symmetric, then this is also symmetric. If G is symmetric, this is symmetric. If G and H are symmetric or commutative, then this is also commutative, and so on. So there are some constructions that would not be symmetric, usually coming from monads. But all these constructions are symmetric. So if you have symmetric coefficients, and if you have symmetric applicative functors, then you combine them using any of these constructions that we have seen, and you get again symmetric applicative functors. And contrafunctors and profunctors work exactly the same way. They have the same commutativity property because, well, we have formulated the commutativity or the symmetry property using this, which is a map, but if this were a contrafunctors, that we would just use contramap here. And this function is an isomorphism, so it is available in both directions. And so we can use xmap as well, because we have this in both directions. Commutativity, or symmetry, makes it easier to prove associativity for applicative functors. I have not used this in my proofs, but mostly because I have specific constructions. I didn't want to assume symmetry. But if you had a commutative applicative functor, that you could just rearrange this into this by permuting A and B and permuting this with this. So you have that, which is almost what you need to prove associativity. You just need to swap FC and FA. And so that's perhaps much less work to do that. You just compute this, and then you swap FA and FC in it, and you demand that the result be the same up to the swapping of types. And that's less work for symmetry, for symmetric code than otherwise. That's otherwise you'd have to first compute this separately, then you compute this separately, But in most cases, it's not a lot of work. It's significantly easier to prove applicative laws than to prove monad laws, as we have seen. So I would like to finish this tutorial with an overview of standard functor classes using category theory. So strictly speaking, this is just kind of a theoretical perspective which doesn't add much practically to programming. It's more or less just a justification. It's an explanation of why these functors exist, why these specific properties exist, and why we have assurance that we have the right laws for them. Here's how it goes. So consider type classes such as functor, filterable, monad, applicative, contrafunctor, and so on. Each of these, when we considered in depth the laws for them, we found a function with type signature that looked like a lifting. And by lifting, I mean it was a function of higher order that took a function like this and produced another function. And the function on the left was of one type, and the function on the right was of a different type. And on the right, it was in the functor f. So always this lifting took something and produced a function from fa to fb. So it took this, produced fa to fb, or took this is flat map, produced fa to fb. This is app. It took this, produced fa to fb. Contrafunctor took this, produced fa to fb. This should be x map rather than die map. I will fix this in the slides. It took something, it gives fa to fb, and so on. So this is what I mean by lifting. It is this kind of function type signature that takes some kind of function as argument and returns this kind of function, fa to fb. Let's look carefully at the types of functions that are taken as arguments by these liftings. All of these are functions of types contain a and b. They're functions from something to something that contains a and b in some way. This is what we considered to be a category in the previous lecture. Namely, it's a description of what is the type of a function that we twist. So we kind of twist the function type. We don't just take a to b, like here. We twist it a bit. We add something on top of a to b, or we can even reverse the arrow. We can have b to a instead of a to b, or we have a to f of b, or we have a to 1 plus b, or we have b to 1 plus a, or something like this. So it's kind of twisted. It's a twisted function type. And so all these liftings take a twisted function type and give me a function type in the functor. So functor transformation. Second thing we notice is that when we looked at the laws that need to be required for these type classes, each of these strange twisted function types had identity and composition laws. There was always a way to compose two of these and get another one of those. So, for example, we composed a to b and b to c, and we got a to c. We composed a to 1 plus b, b to 1 plus c, and we got a to 1 plus c. We compose a to fb, b to fc, we get a to fc. We compose f of a to b and f of B to C, we get f of A to C, and so on. We compose functions of this type. Also, we had an identity function of this twisted type. Here it was the ordinary identity. This was a pure option that creates, so 8 goes to 0 plus A, so it creates a sum of A. This was the pure function of the monad. This was the pure of identity. This is identity. We did not consider those things in this way, but they have exactly the same structure. There's an identity function of this twisted type, and there's a composition for functions of twisted type. So in our simplified definition of a category, that's what category is a twisted type for functions such that we can compose these twisted functions and we have a twisted identity. So here in the applicative, I denoted it like this. This is the twisted identity, and this is a twisted composition. And so, for example, a function of a value of type fa to b can be composed with other values of type, say, fb to c, and you get a value of type fa to b, fa to c. Sorry. So that's the general scheme of things, it seems. For each of these examples, we have this twisted function type, a twisted composition of these twisted function types, and a twisted identity. And the laws of identity and composition hold. In other words, composition of identity and something is equal to that something, and composition is associative. These are the axioms of a category, the category laws, so to speak. A category is described by saying what is the type of the twisted function that it has. A twisted function is also called morphism. So what is the type of morphism that the category has? This type should somehow depend on A and B. So there must be A and B in this type somewhere. Other than that, we don't know what that type is. It could be many different type expressions having A and B in it. And it better be some kind of function, but it could be like this as well. It's not clear exactly what qualifies as function. Is this a function? We don't know. One example of applicative is a monoid with no dependence of type parameter. That's not a function, strictly speaking. But it doesn't matter. A morphism is just a type such that you have an identity element of this type and the composition of elements of this type, and the type is indexed by two type parameters, A and B. That's all it needs to be. It's just a morphism is a type expression depending on two parameters, and that's it. Each category has its own different definition of what that morphism is. Some categories have names. This category is the plain type category, which is not twisted. It's just a function that is not twisted. So this is the category of ordinary functions. This is the Kleisli category of the functor f. This is the Kleisli category of the functor option. So it's a specific example actually of this, with the option as a specific f. This is the applicative category, but that's just what I call it. There is no accepted name for it, it seems. This is the opposite category, the category of functions with opposite type signature. I don't know what this is called. This is the opposite to option Kleisli. So, the generalization that category theory gives us here is that all of these type classes are seen in one kind of way. You define them by specifying the type of the morphism that defines the some special category that you're interested in. automatically you demand laws, the category laws. You specify identity morphisms. Once you have specified this and demanded the laws of category and also naturality, there must be in all of these naturality laws which relate, like we had here in here, the naturality laws that relate this twisted composition and the ordinary usual F-map. So that must be there, naturality, because we are now, we need to always relate this category and the category we're working with. So, but once you specify these laws, which are always the same laws, so they're not different somehow in each case. They're the same laws, just for a different category. It's a very powerful generalization where you basically say everything is fixed except for the type of the morphism. And you can choose that type in many different ways, and you get different type classes automatically, with all the correct laws automatically chosen for you. Remember, the filterable functor had 4 laws which were kind of ad hoc, if you look at them like that. Monad also had laws that we kind of guessed. Applicative, we kind of guessed what these laws must be. But if you look at those from the category point of view, they're not at all arbitrary. Once you specified this type expression for the morphism type, or the twisted function type, everything is fixed. All the laws are fixed. You derive all the possible constructions for the functors that satisfy these laws. All the laws, for example, for zip and wrapped unit, are equivalent, as we have shown, to the category laws for this category. And the same thing we have shown in previous chapters about filterables and monads. The category laws are equivalent to the laws obtained previously in terms of different functions. So because the category laws are always the same, it's just that the types are different, we have assurance that we found the right laws, that all these classes are somehow correctly defined. We didn't forget some law for filterable. Also, we didn't have too many laws. We have exactly the laws we want. And that's one thing. The second thing we obtain from this systematic picture is we can try to generalize and find more type classes. I mean, we have found these type classes. Are there any more? Have we forgotten some interesting type classes? How do we generalize? Well, in this scheme, the only way to generalize is to change the type of morphism in the category. Let's see. We had A to B. We had A to F of B. We had F of A to B. But we didn't have F of A going to B. We didn't have that. Why not? Indeed, excellent question. And if we consider that as the type of the category's morphism and demand that these functions, twisted functions or morphisms, have a composition law and identity law, we obtain something called a comonad. We have not yet considered comonad, and we did not find any other motivation to consider it, but this is a motivation that kind of falls out of this consideration. So we have A to B. This is A to FB with some specific F. We could take some other specific F and see what happens then. Maybe it's something interesting. And generalized filterable. So from option to something else. Maybe it's useful, maybe not. Monad. Applicative. Now, doesn't seem to be any other way of putting F on here. We already exhausted everything. We have A to B, we have F, A to F of B, F of A to B, FA to B. Now let's reverse. We have B to A. We have B to 1 plus A. What about B to F of A? What about F of B to A? And what about FB to A? I tried some of them and they don't work. So actually, this scheme does not always work. So you can't choose an arbitrary type expression here and expect it to work. In what sense do I say that it does not work? In the sense that you cannot find a composition law for this category that would at the same time fit with this scheme. So, because what you want is not just some arbitrary category with some arbitrary composition law, but you also want to lift it then to your functor. And that's what doesn't work. So you basically find that there aren't any functors that satisfy this property. Another thing that is not great about it is that some type classes don't seem to be covered by this scheme, such as, for example, contra-applicative and profunctor applicative. I haven't been able to find a formulation of them using this scheme. So maybe there is a trick that I'm missing, but right now, and especially since, for example, contra-applicatives don't have an app. They don't, so you cannot write it like this. So, you could think contra-applicative, since contrafunctor means this category, and applicative means this category. Contra-applicative means F of B to A. No, so you can't have this kind of thing with F of B to A. So the conclusion is, we have a very interesting and general scheme that shows that there are some type classes, like these, that are in some sense natural. There's some sense they are all part of one approach, which is define a category, lift from that category morphism to this morphism for some functor f, derive the laws from the category laws that must have here. The liftings laws are functor laws. They're fixed as well. I didn't talk about this, but the laws for this are fixed because it's just a functor from one category to another. And so the laws are identity must go to identity, composition must go to composition. So again, no freedom in choosing the laws. We have fixed laws here, fixed laws here. We derive then what are the properties of the functor f such that these laws hold, and we formalize this as a type class. So in this way, we can make a case that all these classes, all these type classes are in some sense standard. They are all obtained from the same method, and their laws are fixed. So we have good assurance that we have found the right laws and the right type classes. And we can generalize. So comonad is one example that follows from this scheme with this choice of the morphism type. Some possibilities like contramonad, when you try to do monad and you do B to F of A, for example, doesn't seem to work. Some classes like contrafunctors, applicatives, don't seem to be covered by this scheme. But other than this, seems to be a very powerful generalization and an elegant way of conceptualizing and justifying that the laws are correct and understanding why the laws must be like that and how to analyze those functors. And so for each of these types, we have thoroughly analyzed what functors have the properties that they have, that they must have, and in a later tutorial we might do the same for comonads. So this is what category theory brings. It's kind of a conceptual generalization. It is not so much in terms of specific code that we couldn't write until we saw this table, but in a certain sense it shows a direction in which we could go on, and that's so far what I found category theory gives. So to finish off this tutorial, here are some exercises for you along the lines of what we have been doing. And some of these exercises require proof and others don't, and I indicate where. So here you do need to prove, and here you don't, and here you don't, and here you do. Good luck. So this concludes the tutorial in chapter 8.